All right, so welcome back. Hello. I'm posting this video mainly to get you caught up through today, October 28th, which is test day for us. I'm actually going to get rid of my blurred background here because it is acting a fool. So anyway, try to go nothing. And we'll see how this goes. Now, let's do a little WL. Oops. Anyway, so I'm going to get you caught up. This is October 28th. I'm going to get you caught up on what we've been doing. Oh, well, my custom background with that WL. It's not a backgroundless background. Whatever. I'm going to get you caught up on what you may have missed. No, what you missed if you were not in class. Beginning on sort of end of Thursday, beginning of Friday, Monday, Tuesday were review days. But let me just lay it out for you. So the video I posted last was on October 21st. That covered actually October 21st, Wednesday, and Thursday, the 22nd. Got us through Lewis dot structures, introduction to polarity, alkanes, alkenes, and alkynes. That video actually put you ahead of Thursday's class. That's all we did on Thursday. We worked on those worksheets, and especially the attached one, which is just a double copy, by the way. It's 2 to a page, which is just more practice. I can show you that in a second as well. All right, I think I'm back going. Yep, so there we go. Over here, you'll notice, let me shrink myself. You'll see that we're on their class page. Doesn't matter which class page I show you, but we're on our class page. We're on the classwork section. And on the day A9 video, we did, so 7, 8, 9, I caught you up through day 7. That was Tuesday. Wednesday, day 9 was Thursday. Breeze through, fly over, polarity. We really did polarity on Friday. We did this material here. We did the Lewis dot structures notes and the group worksheet, which was the double worksheet, 2 to a page. Practice drawing those Lewis dot structures. You'll see some of those revealed as like a key that we did in class. Kind of went over a couple of those. The alkanes, alkenes, alkynes table I asked you to fill out in that video as well. Up over there, actually down there. Anyway, and I asked you to get that one as well. And so you were supposed to practice that yourself and then check it against the key that was also revealed later on in that video, like a minute and a half later. And then polarity is the video. These are the notes, the bonding, polarity, concept attainment that we mostly did on Friday. That's pretty much all we did. We discussed the concepts and outlines of that. And we had the do now that it's actually on the first slide I'm about to show you. So this was our do now Friday. Exam was still posted to a Tuesday. It's now Wednesday, of course, if you haven't gotten that by now. I'll be sending out a message on Remind. If you are watching this today, you'll see that you'll get a message from Remind that gives you kind of an outline of what to look for when you're doing your tests. You're going to do it remotely. You're going to have as much time as you would if you had it in class. As soon as you open that remote, that time is constant, is direct, straight away. So once that time frame opens, that's when you need to do it. If you require some other, there's a window to start the test, but once you start the test, that time frame is fixed. It's going to start and it's going to run. And that includes for the short answer questions, which means you need to do the short answer questions contemporaneous to the test. That means at the same time as you're taking the other parts of the test. You need to do it on your own sheet of paper. And like I said, I will send out information on Remind to you about where to find your login information, how to get to ZipGrade Remote. ZipGrade Portal is what it's called, and you will run through that as you see fit as you go through it. Now, if you need any other accommodations, you need to let me know because we're coming up against the end of the 9 weeks. It's going to put us against the clock. That means there's going to be, if you don't get things squared away, we're going to talk about have to get into incomplete territories, things like that. So we just need to approach that at a later date. So first thing is that. This do now said, how can we use Lewis dot structures to predict whether a compound is polar or not? Well, Lewis dot, that's just what we practiced it. What we ended up doing is looking at Lewis dot structures, thinking about how they might be arranged in 3D geometry. Based on some of the slides, we did poke through some of those slides where I talked about the lowercase delta symbol shows polarity, polarity, partial charge, partial difference in poles. Anyway, so we will, I'll look at those slides again with you, but just know that I'm going to go transparent background. Just know that that's kind of That's what we did. Was we went through a couple of those, and we just use Lewis dot structures. Imagine them in a geometric sense, a 3D geometry, and/or looked at what could happen if it were single bonds. Single bonds can flex, and then when they flex, does that lead to an area of naturally more electron, or more negative area and a more positive area? Those are governed by the presence of extra electrons. The presence of extra electrons would be like things like, if you have an area where there's an accumulation of extra electrons, like extra dots, or the bonds there's triple bonds or double bonds, those would be areas of extra electrons. But like I said, I'll look through those notes, and we're a little hampered because I can't undo them. I'm just showing you the board notes and walking you through what I did. So just understand that if you have questions, you need to post them. You need to send me those questions. We need to wrestle with some of these topics beforehand so you can feel confident going in the test. Understand that test window will be open for a period of time for you. But as soon as you start it, you've got to finish it. So just understand you get your questions out ahead of time. Make sure you look at the review. I'll post the review as well for you to this posting, and should be good to go. Anyway, Lewis dot structures help us predict. We looked at some formulas for naming some hydrocarbons and compounds. We just practiced some from that table. You should practice by looking at ones, just covering it up and saying what's the formula or what's the name. That's how you can practice some of those. Or go to the textbook, and I think it's chapter 23 in the textbook that has some of those there as well. Look at the rules that go into that. Nevertheless, we flew through these because these are just practice of other things. Oh yeah, this was the key to the covalent ionic naming cards. It was on what was on the back of the covalent practice worksheet of the multiple practice things. This is the key to it, including the ionic and covalent. So pause on the slide if you need these. They're out of order and kind of out of whack, but you can pause and find the time. Ionic, same thing. Pause, find the time, check your answers. Talked back through hydrocarbons, but we already did that in this on this other video. You can go back through these slides as well if you have any questions. This kind of gives just the theory to alkanes, alkenes, and alkynes and how they're named. How they relate. They're only hydrogen and carbons, so remember, if you're naming those, you might first say, oh, that's a covalent. But it's only carbon, hydrogen. It's a hydrocarbon. It has special names, alkanes, alkenes, alkynes. And you need to look at that and pay attention to that before you do anything else. Then going into Friday, we talked about polarity. We looked at what are the differences between CO2 and H2O, which is balanced, which is unbalanced, which is nonpolar, which is polar. So that's what we did on the board in class, and I'm about to show you that next. So I don't get to show you the nice progression, but more or less I draw the Lewis dot structure here, and then let's see if I can draw on this page for us. So I draw the Lewis dot structure for, oops, is that going to let me do it? Oh, here we go. It's too big of a point. Okay. Draw the Lewis dot structure here for CO2 and for H2O. So I had to follow my rules, counted my electrons, drew my central bond atom, that's the C, drew my central O for the oxygen, drew my single bonds, drew my dots, it was dot, 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 single bond, dot, 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 because that's our normal rules for Lewis dot structures. But then we count our electrons and we're over 16 we're actually at 20, which is too many. So to get rid of 2 electrons from our total, we turn some of these dots into double bonds. So we draw a bond here and a bond here, and I would erase these dots and these dots for this double bond, or this extra bond, and these dots and these dots for this extra bond on the oxygen. So let me do that. And that was the CO2. Similarly, we looked at the one for H2O, and then we decided, well, which one's polar? Well, we can use these Lewis dot structures to predict some things. By the way, this is an underline. This is not a triple dot. It's not a triple bond. Just an underline. That's not an extra dot. Let me erase those two just so there's no confusion. Anyway. So we looked here at our 2 bonds, and we said, well, they look both balanced when you first draw them. But one of the key strategies here on predicting polarity is to say, okay, which one has, if they both look balanced, one is less balanced, we need to be able to say, well, they both look balanced, but we need to say, okay, which one has single bonds? If it has single bonds, it can also flex, so that these two dots here, so the two dots here on this oxygen can trade places with this single bond and hydrogen, and actually swing down and look like this. Cool. And then it's just a matter of taking a look at the dots and just counting them up and saying, okay, now that this flexes, now we see that there's 1, 2, 3, 4 dots on the oxygen. Two electrons are contained in the bond. 2 electrons are contained in the bond, and then there are no dots drawn on hydrogen because it's satisfied with its single bond. Hydrogen don't need extra dots because they just need to get to 2, not 8. So then it turns out here that there seems to be an accumulation of electrons on the oxygen and nearer to the oxygen, and then also not an accumulation of electrons at the hydrogens, which gives it a little bit more positive charge because the accumulation of electrons give this area a more negative charge. Just slightly enough to be considered what's called polar. CO2, similarly, has accumulations of electrons, 4, 4, 4, 4, which at first seems balanced, and then even there's 0 technically directly on the carbon. So we split this sucker down the middle. It is considered balanced. So we would say CO2 is balanced, or CO2 is balanced, and H2O is not balanced, it's unbalanced. And then the first word we would fill in on that worksheet, here on the polarity concept, we would say, we drew these up here, we'd say the word polar means, let me erase my font here, what in the planet? Can I just erase them all together? I don't know how to take away at all. Let's go here. There we go. I can just erase it all in one fell swoop. All right. Then we looked right here. We did those two drawings in these boxes, and we said, okay, polarity basically means unbalanced by accumulation of electrons. Nonpolar means balanced accumulation of electrons. Then the next slide and the next page in the slide that we skipped down to was this picture. We redefined what these were. Covalent compounds do not conduct electricity, but they're between metal or non-metal, but sometimes the electrons can be shared, can be shared unequally. That unequal sharing of electrons gives it a polar feature. If they are equally shared, it would be considered nonpolar. And we looked at some of these the other day. Methane and water. Its polarity allows it to surround cations and anions so as to dissolve things. The polarity and Lewis dot structures give rise to 3D structures. If we compare CO2 and H2O, we notice that there's a balance of charges. These dipoles is what the polarity is called, are canceled on the CO2, but they are not canceled on the H2O, giving this general rise. This dagger image represents a dipole pointing in the negative direction, positive at the plus side or the handle of the dagger. So CO2 is symmetrical and therefore nonpolar. Symmetrical is another word you could add to your nonpolar box. Polar would be an unequally sharing of electrons. We can determine this using differences in electronegativities. If there's a stark difference in electronegativity between the atoms, like oxygen and hydrogen, then that creates the conditions for polarity. It gives it the reason to actually be more polar. Of course, geometry matters as well. B and F bonds are polar, but it's because the whole thing is symmetrical, it is nonpolar. That's one of the practices from the worksheet. I can show you that drawn in a minute. Actually, here we go. Okay. Actually, we get below that, we look at the picture that was in the slides. Let me go back to the worksheet here. We look at this picture that was on your page, and I said, all right, studying these, knowing these are polar and these are nonpolar, what would you say about it? Well, I prompted the students, and they would just say that, oh, polar still seems unbalanced. Well, what do you mean? What you mean is there's a slight accumulation in one area of electrons. So that goes as the definition. Pause and re-listen if you need to, or re-watch that to write down the definition. It's the slight accumulation of electrons in one area over another of a compound. Okay, and then over here, nonpolar would be in a balance, equal, uneven spread or spacing of electrons in the entire molecule. Okay, and those definitions appeared also here. Accumulation of electrons, slight negative and positive charge like HCN here. You can count the electrons. See the partial negative, partial positive. That's what those delta symbols mean. Nonpolar means that either they're dipoles that exist and they cancel out, like these H to C does create a dipole moment, but they cancel out to each other. Notice here the addition of vectors. Rewatch that and listen if you need to. Any part of this you should rewatch and go back and see because I'm kind of breezing through. Then on the back of that worksheet asks you to predict, draw a Lewis dot structure, and then predict which one you think is polar versus nonpolar. You circle the polar one. I want you to pause now and go complete that first, Lewis dot structures, and then I'm going to go through the key for those. And then if you have questions, please post those questions. Please post those questions to this video. Anyway, so pause now because I'm about to go over the key. All right, so the first one here is SF3 is considered polar because the F's are single bonded. They appear at first balanced, but the single bonds allow the F's to flex, which give the negative charge appearance. So it is polar. Singles flex. BF3, the double has a double bond in order to accomplish the rules of drawing Lewis dot structure, which makes it look like the inside of a peace sign. NH3 has single bonds, so can flex actually in three-dimensional space like this. Nitrogen, hydrogen, 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 and those flex down so that this is a negative area and this is positive. So NH3 is polar. Then we say PCl3 is polar because of the opposite reason. P now is more positive than the Cl's, but it also has single bonds, so can flex just the same way as the NH3, except this time the Cl's are the negative area and the P is slightly less negative, so called positive. That makes it a polar bond, polar compound. Cl2 looks balanced as it's written Cl2, as its Lewis dot structure is drawn, it just plain old is polar. Or nonpolar, excuse me, nonpolar Cl2. And diatomic, don't forget diatomics. Diatomics, you always write. If I mention chlorine, that means Cl2. If I say oxygen, that means O2. Nitrogen, N2. All Honchliff-Bratt. All the halogens, and then H, O, and N. All the halogens, group 17. Honchliff-Bratt is the way it goes. H-O-N-C-L-I-F-B-R-A-T. Those are your various diatomic molecules. Okay, continuing on, CH2Cl2. If you draw this where the H's are opposite each other and the Cl's are opposite each other, you're just presuming a certain balance to it by nature. Instead, look at how it's written, CH2Cl2. So when you draw the Cl central, draw your H's in a row clockwise, just like you would dots, or counterclockwise, and then Cl's around. And you'll notice that the Cl's are in one spot and the H's are in another spot, and that creates a positive area near the H's, negative near the Cl's, polar bond. CH4 actually looks polar, non-polar anyway, it looks too balanced. SiBr, you have HCN, looks polar. This is the best example for the test question, actually, and does. This one is also pretty basic. There's one that's clear and obvious how it's balanced versus unbalanced. This is another great candidate for the test question because this clearly shows in just straight up drawing, I don't have to rearrange anything. It looks balanced because the triple bond and the nitrogen. SiBr just looks balanced even though there are polar bonds. Those whole thing is non-polar because those polar bonds cancel. They're symmetrical. Okay, so we say HCN is polar, SiBr is non-polar. Anyway, and we would need to justify this on the test question. There's one test question where I ask you and say compare these two and say which one is polar and why do you think is polar? And your answer would be something like HCN is polar because there's an accumulation of electrons, which is true of every polar bond, by the way. That's the beginning. HCN is polar because of an accumulation of electrons in one area, closer to the nitrogen or between the nitrogen and the carbon, or in the triple bond, or on the nitrogen. Those are all three ways to answer getting that. So HCN is more polar because of an accumulation of electrons in one area, which is that one area is either on the nitrogen or between the C and the N, or because of the presence of the triple bond or in the triple bond, right? Those are all ways to earn that 5-pointer on the test. So good news, that gets you caught up. The rest of the way here was we just practiced some more naming practice, made up questions from the class. You can go back through these, cover up the boxed answer and try to predict the other one, just like what we did from class. That was Friday and Monday. And then Monday we did some more of that, did some Quizlet Live. Mainly it was just impromptu practice, kind of going over things here and there. Not really reteaching anything, just going over some things that were prompted by students. And then yesterday we played quizzes, Quizlet Live, and all that. What you need to do is do that 24-question quizzes that's attached on Google Classroom. Students might walk in a second. Do that 24-question quizzes. That's a grade. It's a quiz grade. All right, so that concludes it. Please send me questions if you have them. Without interruption, appreciate that. And anyway, go Dogs. Let me know. You've got to talk to me. You've got to keep up with me. You're still in this class, even though you're at home and we're not live streaming. You have videos. You have content. You have resources. Please use them. Please use communication. Be a grown-up. Well, be responsible. Be as grown-up as you can be as you're learning this. We're going to work with each other, but you got to be reasonable. I can be reasonable, but you got to be reasonably attempting it in all form and fashion. So, go Dogs. Let me know what you think.